Okay, let's get started. Hello, everyone. Um, Thanks for joining on Zoom. Sorry I can't be there in person. So we've been talking about bias variance trade-off. And to set things up, we started with a statistical model. Let me just go over it again quickly. So we have the true model, which is how the data is generated, both the training and the test data. Of course, the training data, we put I on the subscript, whereas the test data, we don't have the subscript I. And the true model has some true function f of x, which is arbitrary. And we add additive noise with mean zero, variance sigma squared, and that gives us our true labels. Then we predict those true labels from and these are test quantities. We take our test feature vectors. We have some prediction model, which may agree with the true one or it may not. And that prediction model depends on some parameters beta. We will assume we are using the beta that we have obtained from the training data. And that gives us our prediction y hat, which is hopefully close to y. And the way that we measure how close it is we look at the mean squared error. But the mean squared error that we look at first is conditional on x. So we say for a given test feature vector, what is that mean squared error? In doing so, this expectation, this mean operation, is taking out the averages due to the noise on the test label, as well as any fluctuations in the parameters due to the randomness of the training data, which determine those parameters. But we are treating x as fixed for the purpose of this expectation by conditioning on it. So this is our statistical model. And we also learned, let me remind you of some important properties we learned about expectation. So we have the linearity property. And then we have, if you have two independent random variables, we have this decoupling property that happens for expectation. We have those properties, and then we also we have an important property whenever you do the expectation and you condition on a random variable. It means that for the purpose of that expectation, you can think of that random variable as if it was non-random, deterministic. And so like you can pull that out of the expectation. Another thing we learned is if two random variables are independent, then when you condition on one of them, that does not affect the other, does not affect that expectation. And yeah, we also learned this law of total expectation. So with that background, last time we went through this long derivation where we got to use all those properties. And essentially what we were trying to do is we're trying to understand something about this mean squared error as a function of x. And the main result we came up with, which is a super important result, one of the most important results of this entire semester, is that we can factor it into three different terms. The first is the irreducible error. This is something that can never go away, even if you have a perfect predictor, even if f hat equals f. And this has to do with the fact that there's unpredictable noise in y that you will never able to predict with y hat. Then we have a bias term, squared. And this bias term is telling us how good is the prediction error on average for a given x. And then finally, we have the variance term over here, which is saying how much does the prediction y hat deviate from its average? This is y hat. How much does that deviate from its average squared on average? So those are the three terms. And this will give us a lot of insight into how to design machine learning models. Essentially, what we'll see is that when we change different parameters, such as the model order, you can increase or decrease the bias, you can increase or decrease the variance, and what you want to do is you want to get the best trade-off between these two parameters. Generally speaking, as you make the bias small, the variance goes up. As you make the variance small, the bias goes up. And so you want to get a good trade-off between the two. So, so I think one of the best ways to understand this is through this demo for this unit, which is the true function in this case. And this is, okay, so the true function, yeah, this is just a polynomial function of a single scalar feature x. And so ideally, our model would give us this prediction, for any given x, like if x was 0.5, we would want it to give this prediction here, and so on. What we're showing here is the results of an experiment where what we did is we had training data, and with that training data, we would, in this case, when d equals 1, we train a linear predictor, which is going to be a line. And we do this over and over again, 100,000 times. Every time we have a new training data set, we get a different line. And what we're showing here in the solid green curve is the average of all those 100,000 lines. And essentially, okay, and then for the, yeah, so that's the average of the 100,000 lines. And then these error bars are showing us essentially the standard deviation, square root of the variance over those 100,000 experiments. And so what we can do is we can look at an example of this. Well, actually, the plot is not going to show this part, but from the plot, we can get a sense for those two quantities. So remember, the bias is the difference between the average y given x, which we know is just this quantity fx, which is this red line, and the average prediction, which is the green curve here. And so if I focus on a particular x, let's say I'm focusing on x equals 0.5, then it's saying that the difference between the red and the green, that is the bias, and the variation of the green around its average, that is the variance. Well, we would have to square those error bars to get the variance. And so when you look at an x here, you see there's quite a bit of bias with this x. But if I happen to look at this x over here, you can see we got kind of lucky. There's really no bias at that one particular point there. So this is sort of an illustration of the bias and variance as a function of x for this particular case of polynomial model where the true polynomial is cubic and the approximate one was just linear, d equals 1. So then we can go over to what happens when d equals 3. So now we're actually designing a cubic polynomial, but we don't know the true one. So with our training data, we try to design one, and we do this 100,000 times. We were going to get 100,000 different variations on cubics. And when we look at the average of across those 100,000, we get this green curve. And what's kind of striking here is that the green curve is sitting exactly on top of the red curve. That means there is no difference on average between y and y hat. There is no bias when d equals 3. But when we look at the variance, that is how y hat deviates from its average value, we can see that the variance, if you look closely, the variance has gone up. These error bars are a little bit bigger than those. And when you go to the edges, these are even bigger than these. So we can see here, as we went from here to here, the bias went down, but the variance went up. And we can go one step further up to d equals 14. And sort of amazingly here again, no bias. So here we're training 100,000 different 14-order polynomials. So each one on its own is going to look wiggly. And when you average those 100,000 of them, what's amazing is that you get something which looks cubic, and it is essentially right on top of the true model. So here again, no bias, but you can see the variance got much larger. The variance in the middle got larger, but the variance on the edges got much larger. And so from the point of mean squared error, you have to look at the bias squared plus the variance. So over here, our bias is large. So when we square that and we add it to our variance, it's suboptimal. The middle case is the best. The bias is 0, which is great. And the variance is a little bit larger, but it's still, this mean squared error is less than this. But when you go over here to the right, even though it's unbiased, the variance has gotten much larger. So the MSE over here is much worse. And this idea from a different perspective can be visualized as if you're throwing darts or shooting arrows. When you have high bias, that means on average, which would this, in this case, the average of your throws is here. You can see the average is quite large, but the variance is quite small. And over here, the average is great. It's 0, but the variance is much larger. And this is the best mean squared error when the bias is small and the variance is not too large. So that's sort of directly what's happening in those 3 cases. This is a good time to stop and see if, does anybody have any questions about anything we're talking about here? Okay, no questions. Yeah, this is a super important slide because I think it really does get to the heart of understanding bias and variance and what it means, how it works. So I'm happy to answer questions, but of course, if there are none, also happy to move on. Okay, so I guess we'll move on. So we can go one step further. So this kind of experiment here, this is really looking at the bias and variance conditional on X. So here we're really looking at these quantities. And you might say, like, I care more about what happens on average. I don't care about like a very specific feature X. I don't know what test features I'm going to get in the future. So I just want to know what happens on average. So that means we want to do an average over those X. And then we just get the mean squared error on average, not conditional on an X like we have here. So when we do that, we can actually get some interesting results that even give us a bit more quantitative picture of what's happening here in this experiment. You know, why is the variance going up? Why is the bias 0 here? So, so I'm just going to present the results. There is a derivation in this handout down here. It's a little bit long. I'm not going to hold you guys to any details in that derivation, but it's certainly there if you want to look at it. But I will hold you to the details, sorry, not the details, but the main results, which I'll get into right now. So essentially, in this previous slide, and we were assuming any function f. We didn't say what f had to be. So now let's be a little bit more specific. Let's talk about models where the true f is linear, and the model order of this linear model we're going to call d true, and then also our prediction function f hat is also going to be linear, but the prediction model order is going to be D. So D could be the same as D true or it could be different than D true. So this is a little bit more specific than what we did before, but this allows us to go a little deeper and actually get some more quantitative results. So the first result is what happens in the data starved regime. So this is where the number of data samples is strictly less than the number of tunable parameters in our model. So if you think about the A matrix in this case, the A matrix that you get is going to be a wide matrix. And so that means that when you look at A transpose A, this is going to be a tall matrix times a wide matrix, which ends up giving you a matrix that is not full rank, that is not invertible. So that means if this is not invertible, that we can't invert it, we can't compute the least square solution. And in fact, there's actually many different beta hats that minimize the error, the RSS. And we don't even really know, we can't even really say which one we're talking about. So in this case, which is unusual in machine learning, but not impossible, in this unusual case, there is actually really no clear least square solution. We can't really say much about it. So let's just assume that we at least have an invertible case like this. And we're going to, okay, so this is if we have enough samples. But now let's assume that in our model, the D is strictly less than the true model order. So we're looking at this case here. D is strictly less than D true. Then you can prove that Y hat will be biased and we will be underfitting. And that's one of the things that's proven in that handout. Now, on the other hand, if you have enough data and if the model order here, your prediction model is equal or greater than the true one, now you have a situation where it's possible with the right selection of the beta hats to exactly get the true model. If you use least squares linear regression, Y hat will be unbiased. And in fact, this sort of explains what happened on the previous slide, because as we know, with a polynomial model, we can actually just assign the different powers to different features xij or xj. And so basically, the polynomial model is subsumed under this linear model. And that explains why when the true one was D true was 3, but D is 3 or larger, in both cases, it's unbiased. That's something you can actually prove. Okay, now what I think is the most interesting result here is what happens, what you can say about the variance. So because of the proof that I used, it's sort of a technical reason we had to assume that we had a lot more data than parameters D. But let's also assume that we are in this case where we have the model order D is at least the true one. So what's kind of interesting is that you can prove that the expected variance is D plus 1 over N times sigma squared. So remember, D plus 1 is the total number of coefficients you're designing, N is the total number of data points you're sampling. Sigma squared is the amount of that measurement noise variance. And so the meaning of this is this actually, because this is unbiased, your mean squared error will be this plus the irreducible error. So what you see clearly here is exactly the effect of your choice of D. So if you say my data set is fixed, I have a fixed number of samples N, but I can choose a model order, you can directly see as that model order gets bigger and bigger, your variance just gets bigger and bigger. And this is a motivation for not overfitting, because if you choose a model that is strictly larger than D true, you don't have any advantage. You simply increase your variance, things just get worse. If you can do it, go back to D true, and that's going to be, you're going to have zero bias and you're going to have minimum variance. Okay. From another perspective, you can say, let's suppose that my model order D is fixed, but I can somehow collect more data. Well, as I collect more data, more training data, my variance will decrease. And it will decrease not because of bias, but or my mean squared error will decrease not because of bias, but because of variance. So this is where we can clearly see the benefits of larger training data sets. So here we can see kind of two different things about the choice of D and if you can gather more data, the choice of N. Okay, so this is pretty important conceptually. Any questions on what we have here? Okay. All right, so so here's sort of a recap of what we've seen. We've been looking kind of at a special case of polynomial regression where we're trying to choose the model order D, or linear regression where we're trying to choose a number, model order D again. But actually, okay, so in these cases, what we saw is this mean squared error here. We can write it as the irreducible error plus the squared bias plus the variance. And essentially, if we make a rough plot like this, here's our total error, our mean squared error. And here is the bias. And you can see as a model complexity increases, generally our bias goes down, or squared bias goes down, but our variance goes up. So we want to find the model complexity that's not too small, because if we're down here, we get a high mean squared error because of bias. If we're over here, we get a high mean squared error because of variance. But if we're right in the middle here, we can sort of minimize the total error by getting the smallest sort of trade-off between bias squared and variance. So that's the idea. And this, even though we've shown it for linear regression, these trends hold throughout all of machine learning. And basically, there's a trade-off. If you make your model overly complex, you have the variance problem. If you make your model too simple, you have the bias problem. You really want to go in between. So that's sort of the bias variance trade-off, and it's a super important idea in machine learning. It drives a lot of the decisions we make when we design our models and collect data and so on. All right. Any questions on this? Okay. Okay, so let's see another couple important examples of these ideas that will help us sort of connect back to earlier things we've seen. So one of the things we've talked about are sample estimators. And so in particular, we talked about a way of estimating the sample mean, talked a way about estimating the sample variance. And using this framework we've developed, we can actually understand about the trends you see as the number of samples increase, how those estimators behave. Do they converge to the true mean, the true variance, and at what rate, and so on. So the way we think about this now that we've talked about random variables, imagine we have this random variable, capital Z, that has a true statistical mean, which is the expected value of that random variable. Let's call that mu. And then we have that same random variable Z has a true variance of V. And now we just observe some samples of Z. We don't get to know the random variable. So let's say that we have these independent realizations, n of them, and we're going to use small z's. So we have zi, where I goes from 1 to n. And from those samples, we will want to try to estimate, at first, this mean mu. So the standard way this is done is you simply do the arithmetic average of those samples. And as we learned in Unit 2, we call this z bar. This is the sample mean. So this is a good time to pause for a moment and reflect on the fact that there is a difference between the sample mean and the statistical mean. So the sample mean is just, we have a list of numbers, we do the arithmetic average. The statistical mean is mu. In general, these two things are not going to be equal. We might hope that they're close, but they're not going to be equal in general. So there's a difference between the sample mean and the statistical mean. Okay, so, but what we can do now is we can ask, is this sample mean estimate biased? Meaning, on average, is it true? So another way to think about that intuitively is, imagine I'm doing this experiment where I see these n samples, zi, and I compute the sample mean z bar. And let's say I do this experiment over and over and over and over again. Is my z bar on average correct? Is that on average mu? Okay, so in that case, we're asking this question, is expectation of z mu? And the answer is yes, you can prove that this is the case. And what that means is that z bar is an unbiased estimate of that statistical mean. And that's actually one of the main reasons that people use this. It's a very simple estimator, but it actually works quite well. The details of that derivation are in this handout down here. And this handout is definitely something you guys can understand. It just uses a lot of that, those expectation properties. The contents in there, variations on them often show up in homework problems and exam problems and so on. So while I'm not requiring you to go read it, I think it's probably not a bad idea if you do, is to look through there and make sure you understand what's happening there. I think it could probably help you. So that's one interesting result that you can prove this sample mean is unbiased. Now you might also ask the question, well, okay, it's z bar equals mu on average, but how does it deviate from its average? Is it like wildly oscillating around mu, or is it like very consistently close to mu? And so for that, we would like to know, what is the variance of z bar? And so by definition, we know this is the expected squared difference between z bar and its mean. So you can do this derivation also, and you can find out that the variance is v over n, where v is the true variance and n is the number of samples. And so what this is showing us is that as you have more and more samples to do your average from, the amount by which z differs from mu shrinks. And as n goes to infinity, z bar actually converges to mu. So if you had an infinite number of samples and you did this, you would get the perfect statistical mean. That is called the law of large numbers in statistics. So there's another very important thing that some of you may have noticed here. We derived the standard error, if you remember. The standard error was, we call it the standard deviation, but I'll just write here as a square root of the variance of z divided by the number of samples in our average, the square root of the number of samples in our average. The first time we saw it, we were looking at cross-validation and we had k instead of n, but I told you then that that's a very general idea. It's just however many samples you're averaging, that's the number you put in the square root down here. And when you look at this, now you can see, oh, okay, if I square that standard error, that is exactly the variance over n. So this standard error that we saw before is really just a direct reflection of this very important property here. This is just the standard error squared. So standard error is really just you take the square root of this quantity and that's it. So of course, in practice, when computing the standard error, we don't actually know the true statistical variance. So for this standard deviation thing here, we actually have to use an estimate of it. Because we don't know the truth. So now coming to that estimate, we can actually talk about that as well. Before we go there though, are there any questions? Anything we've done here on the top of the page? Okay, great. So let's say that I want to estimate this variance here, again, just from the sample z. So the way that we originally talked about doing this back in unit 2 was the sample variance. Actually, let me put that in blue. So this is the sample variance, which is the arithmetic average of zi minus its mean, sample mean squared. So here again, we might ask sample variance. This is something that I can imagine doing an experiment many, many times where I draw some samples zi and I average them in this way. I get some number and I want to know, is that close to the true variance v or not? And I can do this many, many times and I can see what happens on average over all those experiments. It turns out, and also you can prove this, that what happens on average is that the expected value of this sample variance here is not exactly v. It's this ratio n minus 1 over n times v. So if n is really big, this number is very close to v. But if n is very small, like 2 or something, you can see this is very, very far from 1. So, so basically, the average value of our estimate is not exactly equal to the average value of the truth, v. It's a little bit different. And so therefore, we would say this sample mean here is a biased estimate of the true, sorry, sample variance is a biased estimate of the true variance. And this is something we talked about back in unit 2, and I promised you that I would explain what we mean by biased and unbiased sample variance. And so here we're finally talking about it. Okay, so this is the notion of this guy is not perfect, and it is in fact consistently a little bit smaller than it should be. And how far off actually depends on how many samples we're using. Okay, now this is actually pretty easy to fix. You can see that it's off by this particular scaling factor. So I could just invert that scaling factor, apply it to this quantity. And in doing so, I would get this. So this is another variation of a sample variance estimator. And essentially all that changed is we went from 1 over n to 1 over n minus 1. And in this case, with this different scaling, you would find that the expected value of this is exactly v. This thing is consistent. This is biased. Or sorry, it is unbiased. So, so if you were concerned about this sort of systematic error in your sample variance estimate, there's an easy way to fix this. You just scale it in a slightly different way. So these are two very popular things. Sometimes people use one, sometimes people use the other. If the number of samples is large, it doesn't make a difference. But if the number of samples is small, it does make a difference. So now it's not quite the end of the story. Or by the way, are there any questions so far? Okay, so it's not quite the end of the story because there's still a question like, okay, I've removed the bias, but is this really a better estimator? Why shouldn't I just always use this? So if we come back to the idea of mean squared error and we say that's maybe what we really care about, then we would like to know what is the mean squared error of this biased sample estimator versus the mean squared error of the unbiased one. And this is also stuff that you can derive. It's a little bit more complicated, but it's nothing that you guys can't handle. And the expressions end up looking like this. And it turns out, when you compare these two expressions, this sample variance of the so-called biased estimator is actually lower. The mean squared error of the unbiased one is lower. So in making it, I don't know if I said it right. This is the biased one. This has a lower MSE than the unbiased one. So in going from biased to unbiased, we tend to face these trade-offs. As the bias goes down, the variance goes up. And in this case, when we put all bias all the way to 0, the variance actually went up even more than the result of the bias squared. And so the mean squared error in the end was even worse. So that's sort of an interesting trade-off too, which gives you maybe more pause in using this unbiased version. Yes, it's unbiased, but it comes at a cost that it's actually the mean squared error is larger. So these are the sort of things you have to think about when you choose which of these you want to use. Okay, any other questions on anything here? All right, if not, we're getting close to the end. So just to recap what we've been talking about in this unit, we've been talking about model order selection. And that problem, for example, if we're talking about linear models, we're talking about choices like this. Do I use one term? Do I add a term to that? Do I add yet another term and so on? How many terms do I add? But you might say that, well, this is still kind of constrained because maybe instead of just sort of, adding this third term, maybe what I also want to do is I want to get rid of the first one. Maybe I want to use just those two, or maybe I want to use the first and the third and get rid of the second. So maybe the problem I really care about is figuring out which subset of features to use, not just how many, but actually which ones. And the problem of which subset of features to use is called feature selection. But this is a more challenging problem because there's a lot more choices to make. When you think about choosing the model order, it's just sort of one scalar. Is it small or big or somewhere in between? When you think about choosing which subset of features, you have way more options. Does anybody see how many choices we have if I want to choose how many or which pattern of features to use?
Is it
Would it
in?
be
So, okay, here's one way we can think about it. So for each feature, whether we use it or not is like a binary choice. So we could imagine, and to that binary choice, for example, I could assign the number either 1 or 0. And for this feature, I could also assign the number 1 or 0. For this feature, I could also assign the number 1 or 0, depending if I use it or not. So at the end of the day, I have d binary digits. How many different, d-length binary words can I make?
2 to the power of n?
2 to the power d. Exactly. 2 to the power d is how many different ways, if I have d total features here, how many different ways I can select subsets. I can select, none of them, all of them, or many, many things in between. So, so that's the challenge now, is that for a lot of our prediction models, D is not a small number. If D is a small number, like less than 10, maybe even less than 20, the number 2 to the power D is it's not insurmountable. But if D is extremely large, then 2 to the power D is a number that there's no way you could ever evaluate all those choices. So then you need to start thinking about other ways to approach this problem. And that's exactly going to be the subject of the next unit, is how do we go about that choice? So without further ado, are there any questions on anything here? If not, this is exactly just the lead in to the next unit, unit 4. So let's move over to unit 4. And okay, so we'll come right back to the technical topics, but let me first introduce the demo for this unit. This is a real data set. This is again another famous data set for machine learning classes. It's about PSA testing. PSA is an indicator of prostate cancer. If you're curious if you have prostate cancer, the first thing the doctors do is they measure your PSA. They take a test and they look at the value. So this particular study, where the data comes from, there are 97 different participants. So that's going to give us 97 samples. And they measured 8 different biometrics for those patients. And so there's basically going to be 8 features total. And so that number is small enough where 2 to the 8 is something we can, if we want, we can actually look at all the different possibilities. But basically, from those 8 features and 97 samples, our goal is to predict PSA, see how well we can do. But that's not the only goal. The second goal is to figure out, among those 8 features, which one of them are most important. So this is sort of what you care about if you're doing science. You're not just trying to predict the answer, you're trying to understand what's going on in this case. So we can actually use machine learning to do science. And we can do that by essentially training predictors and seeing, if I can train a predictor that is using some, but maybe not all of these features, which of those combinations of features gives the best prediction? Those are the features that matter most. So that's the idea behind feature selection. Okay. So I think I covered all this. And the data is something we can download off the internet. And so let's just start out with what we know how to do, which is linear regression, using all the features. So okay, so our linear regression model is, as we know, y hat is beta 0 hat, intercept term, plus beta 1 hat x, and so on, all the way up to beta d hat xd. And so again, why are we using linear regression here? Well, actually several reasons. So the first reason, we know how to do it. It's least squares. We learned about it. We in fact know how to use scikit-learn to get the answer. We can now do this in really just a couple lines of code, but that's actually not the only reason. The other reason people use linear regression for these types of problems is that you can actually figure out which features are important just by looking at the coefficients alone. The idea there is that if you find some of these coefficients have a very large magnitude compared to others, those ones should be more important. Now, of course, if you're going to do this, you have to normalize the features themselves so that all the features are on the same scale. And that's easy to do, and we'll talk about that more in a moment. But assuming we've normalized so that all these xi's or xj's are on the same scale, then you can do your least squares fitting, look at the remaining the coefficients that come out, and if you have one coefficient that's very big, that means that feature is very important to prediction, whereas if another feature is very small, it means that's not really useful to prediction. So that's the idea here. Larger magnitude means that feature has a larger effect, at least if the features are scaled. And so we also learned about a way of learning, like, if I train a predictor, how good is it? And we know it's not just what happens on the training data. It's easy to train. If you have enough coefficients, you can always train a model that perfectly predicts your data. So here, it's, as we saw before, we want to do cross-validation. We want to train on part of the data set and test it on a different part, and that's going to give us a much more robust indicator of model performance. We also learned a nice way to do that is k-fold cross-validation. So we saw a very manual way of doing it. It was this 2 nested for loops. It was like a whole page of code. Well, not surprisingly, scikit-learn has built-in ways of doing this where you don't need to write all that code yourself. And this is one of those methods. We'll see several. But this one is called cross-val score. This is what this function does. It's not going to do any like grid searches of parameters D. It's just going to say, give me a model. I will use k-fold cross-validation to train it with part of your data, test it with the remaining part of the data, and I'll do that k different ways, and I'll give you, on average, here's, and I'll even tell you the different folds and so on. So that's what cross-val score does. You don't need to write any for loops. Everything is just done, under the hood. You have to tell it a couple things about what kind of cross-validation you want to do. And so we're actually using a kind called recursive k-fold, where you see, if you do k-fold cross-validation once, the results you see are going to be dependent on the particular random shuffling that you used for your data. And so one way to make it a little bit less sensitive to that random shuffling is you repeat the procedure a number of times for different random shufflings. And this is going to be more computational effort, but it's going to give you slightly more robust answers. And so that is something we happen to use here. And then the other thing, when you do k-fold cross-validation, you have to say, what kind of criteria am I using? So we've been focusing on things like RSS, mean squared error, and that's what we're going to use. We're going to use mean squared error here. Now, the way that scikit-learn is set up is you tell it the score. And all the scores in scikit-learn are defined so that when the score is higher, that means the prediction is better. But if you think about mean squared error, it's kind of the opposite. We actually want our mean squared error to be small. So we can't use mean squared error directly as a score. So what scikit-learn does is they use negative mean squared error. That now gives us a valid score. The best you could be, the highest number is 0, but you could have something below 0. And so that's the score we're going to use. So essentially, we set this up. Scores here is going to output across the folds we've tested. It's going to give us a bunch of scores. And now we're just going to look at the mean of those scores. We're going to negate this negative, and that's going to give us the mean squared error of our sort of default model, where we're using all the features 8. And we find that we get mean squared error of 0.404. So what we'll try to do as we go through this unit, we'll learn about different ways of doing feature selection. We'll see, can we do better? Can we reduce our mean squared error by using less features? Because we know from the bias variance trade-off that if I remove the features that are not important, I will reduce my variance, which will reduce my mean squared error. However, if I remove features that are important, then that will affect my bias, and it will actually increase my mean squared error. So what I really want to do is I want to remove the useless features, but I want to keep the most useful features. That's going to give me the best mean squared error. That's the kind of feature selection I want to do. Okay, so that's the setup for sort of what we're doing in this unit with this data set. Are there any questions so far? Okay, if not, let's start talking about some of the methods. So yeah, so as I just mentioned, as we learned in the last lecture, if we use more features than needed, we get an unusually or unnecessarily high error variance. If we use too few features than we really need to predict the trends in the data, we're going to get a large bias. Both of those are bad, so we want to use just the right subset of features. That's the goal of this unit. And what we also learned about is that there is a sort of brute force approach, which is the following. If you can manage this, you look at every one of those 2 to the power d possible subsets. For each of those, you do cross-validation, maybe k-fold cross-validation, and you compute the mean squared error. And now over all those possibilities, you would just choose the one which has the lowest cross-validation error. And so that is what we call exhaustive search, and that is the optimal method. So that's sort of an important idea. The trouble is that many problems we just can't afford to do this. There's too many features, not enough computational power to really do this. So if we can do this, that's great, but usually we can't. So we're going to learn about 3 other methods in this unit. First, stepwise selection. Second, feature ranking. And third, some regularization-based methods. And we're going to spend most of our time on these latter methods, which are going to teach us a few other super important concepts. So let's start with the first class of methods, stepwise selection. So these are actually really practical, good performing methods. They go like this. There's basically two ways you can run this method. So forward selection, in this case, you gradually build up a model starting from scratch, starting from nothing. So at the very first step, what you do is you say, I'm going to look through each of my D features one by one. And I'm going to use one feature at a time, and I'm going to compare the cross-validation RSS or mean squared error, and I'm going to find which one has the lowest mean squared error cross-validation. And for that one single feature, I'm going to say, great, I'm going to keep that feature. I'm going to add it to the set of features that I'm definitely going to use. Then you go through the remaining coefficients, the remaining D-1 coefficients, and you look for which one can I combine with the feature I cut from the last run, so that pair of 2 features gives the lowest RSS. So I go through all those possibilities, do cross-validation, and finally I find, okay, this is the best feature to pair with my original feature. So now I add that to the list of features I keep. So now that list has 2. And I continue on. Now I go through the remaining features to find which is the feature that I can combine with those first 2 to get the best 3 features. And I keep doing this, as long as my performance is getting better. But as you can imagine, eventually, as you start to take too many features, okay, so maybe let's back up for a second. So when I use a single feature, it's a very simple model, right? It's probably not going to be enough to really capture the trends in the data. So as I add the next feature, probably the cross-validation performance is going to get better and better and better. That's as your bias goes down, your bias squared goes down, mean squared error also goes down. But eventually, bias is going to be small enough, and as you bring in new features, your variance is starting to increase and starting to dominate the mean squared error. And at that point, you'll see your mean squared error going up, and at that point, okay, I've started taking too many features. So you can stop then. You don't necessarily need to go, and keep going to look at all the features. So that's generally how it's done. You keep adding one by one new features until you start to see that the RSS starts to increase. And maybe even you stop before then. Maybe you say at the beginning, I have a maximum number of features, and that's all I want to use. There's different stopping criteria that you might want. So that's the basic idea behind stepwise selection. First single feature, add another one, and so on, repeat, and so on. All right. Is this making sense? Any questions on forward selection? Okay. So there's another option, which is backwards elimination. So here you start with all your features. You turn them all on, and then you go through them and you think, well, I'm going to remove the first one, run CV, see how that does. Put that back. What if I remove the second one? See how that does. So I'm removing features one at a time to figure out which is the single best feature to remove. As soon as I figure that out, I say, from now on, I will never consider that feature again. Now, from the remaining features, I again remove one of each, one at a time, and I figure out which is the next best feature to remove. and I keep collecting features that I will never use. And as I do this, generally speaking, to start, you'll see your variance start to come down, your mean squared error start to come down as you get rid of these least important features, the ones that are not really helping you at all. They're not really affecting your bias, but they are affecting your variance. So, but eventually, once you start to remove a lot of features, the features are important. And now when you take a feature out, your bias really goes up. And so as a result, your variance has gone down maybe a little bit, but your bias has gone up a lot more. The variance went down. So your mean squared error has gone up. So you eliminate these features until you see that the RSS starts to increase, and then you stop there. So that's another approach. Use all the features, remove one, repeat until this is increased. So, depending which one you use, it depends how many features you have. It depends if you think like, I probably need them all, and I'm just trying to figure out if there's like a few that I want to remove versus like, I probably only need a couple. So it's really, I don't want to have to start with all of them and go through this lengthy process to get down to a couple. So those are the couple options. Any questions on backwards elimination? Okay. So both of these methods are not optimal, they're suboptimal. One way to understand why that is that in both cases, when you either, accept a new feature in forward selection that you will use forever, or remove a feature in backward selection, you're sort of making a short-term or myopic or greedy decision. It could, it could be that even though it seems like this is a good choice for right now, that later on, if you were smart, you'd realize, oh, actually that feature was important. But the problem with these methods is that once you accept or remove a feature, you can never go back and change it. That's just how these are set up. So even though they work pretty well, they're certainly not optimal. And they are implemented in scikit-learn in this sequential feature selector. Pretty easy to use. Okay, so that's stepwise selection. Any questions about that? Okay, so let's talk about.
Yeah, I have a question.
Yeah, sure.
So just between the forward and the backward eliminations and the forward selection, um, like looking at it, I think both options seem like would give us the same kind of result. Like both methods seem like if they're bad, both of them are bad. If they're good, both of them are good. Like, is there any option? Is one option better than the other?
I would say generally it's, I mean, you could even use them both. And, generally speaking, they're not necessarily going to agree. They might agree, they might disagree. It's usually more of a computational issue. Like if you have tons and tons of features and you really want to just use a few, it would take a lot of effort to start with tons and get down to a few. And so you would just say, let me start with none and build up a few. On the other hand, if you feel like, probably all my features are pretty useful, but I just want to check to see if there's one or two I could remove, then computationally it's going to be easier to start and to do the backwards elimination. If you, and like I said, if you had time and to do both, you could try to do both and you could see, do I get the same result? If so, you might even feel more confident about that result. But yeah, it's usually computational that how you choose between them. Any other questions?
Good, thank you.
Sure. Okay. So here's another approach. This one is, we can start by motivating by, let's say, maximizing correlation with the target. So this is kind of more of an intuitive approach where you'd say, actually, if you think back to linear regression, when you had a single feature, we saw that R squared was directly proportional to the cross correlation rho XY. So like the more correlated the feature is with the target, the better your R squared was. It's just very directly. And so you might say, okay, that's something we should want in more generally, like we should want our features to be correlated with our target. So, but what you could do is you could look at every feature individually, compute its cross correlation with the target, and you could just rank them from like, these are the most correlated, these are the least correlated. And now that you have these features ranked, now it's actually a model order selection problem where you could say, okay, do I use the first most correlated one, the first two, the first three? And this model order selection problem is very tractable. We can just go through that choice. It's, the number of the order of complexity is D versus 2 to the power D. So by ranking, we can make the problem much simpler. Now, the thing is, this doesn't actually work as well as you might think it does. And there's even some intuition we can get, like maybe I have two features that are both highly correlated with my target. In fact, what if I have two features that for some reason are actually identical? So clearly, I want to get rid of one of them. I don't need them both. But if they're both very highly correlated with the target, then this method would actually be very inclined to keep both of them. So as you can see, it's not really just about correlation between single features in the target. And that's what this univariate statistics idea means, is that you're really looking at single feature at a time, comparing that with the target. You're not looking at your features as a whole, how they work together with themselves. And that's one of the reasons that these techniques don't actually do that well in practice. And there's ways you can try to fix it. You can say, okay, I care about cross correlation with the target, but maybe I also care about minimizing correlation with other features and so on. And you can maybe get it to work a little bit better, but I haven't found these methods to work super well. And you can also say, well, maybe correlation is the issue. Maybe there's a better statistic between X and Y that I can consider. And there are many. You could look at various statistics. It's okay if you don't know what these things mean: mutual information, F values, P values, and so on. There's all sorts of things you can do. And this is all implemented in scikit-learn. But generally speaking, in my experience, these things don't really work all that well. So it's something to think about, but it's probably not the go-to strategy to use. Okay, so that brings us to the very last topic that we're going to get into, and essentially, it's called regularization. And we don't really have time to get into it, but it's a perfect place to stop. So on Wednesday, I will hook back up on Zoom. I'm still going to be out of the country, so Wednesday, regular time, we'll start here and we'll learn about regularization. All right. Let me know if you guys have any questions. If not, I'll see you guys on Wednesday.
All right, thanks, Professor.
Sure.